I'm Lee. In this video, we are going to look at another ADT called the priority queue. A couple of weeks ago, we learned about the queue. Queue is a first in, first out, position-based ADT. So which means when you add something, it will be added to the end of the queue, and when you remove something, it will be removed from the front of the queue. And priority queue organize items by priority. So when you remove, you're going to remove the item with the biggest with the highest priority. So that's how priority queue gets its name. Like when you serve the item with the highest priority. So now let's think about the operation here. So to add something, you need to add it to a position so that later on you can remove it first. So how to implement it? Let's think about the data structure. One possibility you can think of is, I think that's array. So that's our old friend array. So if you use an array to implement it, to implement priority queue, that means you could organize this array by the priority. Like the biggest one will be the last element of the array. That makes sense because this makes remove very easy to implement and very efficient. For example, it could be like 3, 5, 9. If I only have 3 items in the priority queue, in this case, in this array, and the priority is 3, 5, 9. So for the remove operation, you just need to get rid of 9. You can just simply decrease the index. If you add another item like with priority as 1, then you're going to have to add it here and shift the array down. So that's an array implementation. As you can see, you can make remove very efficient, but for the add, you have to shift the array. So that could be a big O log n performance. And similarly, you can think about the implementation for linear linked list, for a sorted linear linked list. Again, you can make remove very efficient because that's the highest priority one. But for the insert, you have to keep it the sorted order. So that will be a big O n, the linear efficiency here, the linear performance here. So now let's think about some other data structure we learned that include binary search tree. So for binary search tree, if you organize the items by priority, you can easily get the biggest priority one. That will be your rightmost child, and that one it's easy to remove, and when you add, it's easier to add. So the performance will be big O log 2 but the assumption will be this is a balanced binary search tree, and that's a big assumption. So, and in this video, we're going to look at another data structure and something called a heap. And what is a heap? Let's take a look. Now you see the heap looks like a binary search tree, but at this moment you should realize it's not a legal binary search tree. Yes, this node has 2 children, but the order doesn't qualify it to be a binary search tree. So let's see, this is a legal heap, not a legal binary search tree, because you see 6 is greater than 10, but it's a right child. So for heap, the property goes this way. The children has to be less than the root. So that's the only requirement. But between those 2 children, they don't have any relationship. As long as they're both less than the root, that's fine. So let's take a look. For 3, this is a legal heap here because it got no pointer for the left child, no pointer for the right child, so got empty left subtree and the right subtree, so that's fine. And now let's take a look at 9. So 3 and 2, both of them are less than 9, so that's a heap rooted at 9 here. And now let's look at 6. 5 is less than 6, so that's good enough. And now let's look at the 10 and the 9. Both 9 and 6 less than 10, and both this whole tree and this whole tree are less than 10. So that's a legal heap. Alright, so the property for heap will be both children have to be less than the root. And also another thing about the heap is about the shape. It's always a complete binary tree. It's not a binary search tree, but it's a complete binary tree. So let's try to remember what is a complete binary tree. A full binary tree means this isn't a full binary tree because this one we have to have a right child to make this one a full binary tree. A complete binary tree's definition is at this level, so n minus 1 level, that it's a full tree. But for the last level, the leaf will be filled in from left to right. So this is a complete binary tree. A complete binary tree gives us the advantage of the shortest height. It's log 2 to n. So, and now let's try to connect this one with priorityQueue ADT. Remember, in priorityQueue ADT, we always remove the item with the highest priority. Okay, so that's something we really care about. Okay, then when you look at this heap, the highest priority is always the root. So you always just remove the root. So let's take a look at how are we going to implement this one. So for the remove operation, if I'm trying to delete 10, so let's think about it. Delete 10 won't be easy, so let's swap it with a child, with a leaf. Okay, so this is what we're going to do. We're going to swap it with the rightmost child, the rightmost leaf. In this case, that will be 5. So we're going to put 5 here. So 5 will be here. And if you put 5 here, then just delete this node. Alright, but now here's the problem. Now you leave this heap as a legal heap now because 5 is less than 9 and 6. So what do we do here? So we need to move 5 down to its legal position. So when you compare 5 with 9 and 6, it's obvious 9 should comes here. So this is what you have: 9, 5, and 6, and 3, and 2. Alright. So now let's try another one to see if you get the algorithm. So for the next remove operation, we are going to remove 9. So what do? We swap it with the rightmost leaf, which is 2. So, okay, we swap it with 2, then delete this one. Alright, so now next operation will be we put 2 at the legal position. So you compare 2 with 5 and 6. So you have to swap 2 with 6. And now that leaves us a legal heap. I hope you get the algorithm. So the algorithm will be to remove an item in the heap. You always remove the root item because that's the item with the highest priority value. So you swap it with the rightmost leaf. And after you swap it, you can delete that rightmost leaf. And you just need to go down the heap to test if it's at the legal position. So after the remove operation, the legal one will be the biggest priority item should be at the root and still leave it a legal heap. Okay, so that's the remove operation. Now let's take a look at the add operation. So for the add operation, let's see, let's still keep it this way. Let's say we have 10, we have 9, we have 6, and you see it's a legal heap. And for 9, it's a legal heap too. Okay, how about now if I'm trying to add 9, we already have 9 here. So how about let's try to add 8. How do we add 8? I'm going to keep it a complete binary tree. I have to add it here as the rightmost child. So just to keep it a complete tree, you just add from left to right for the last layer. So we add 8 here. Then we need to put 8 at the rightful position. So you compare 8 with 6. So you need to say, oh, you two need to swap. Okay, then you compare 8 with 10. You two need to swap. Oh, I'm sorry. You compare 8 with 10. That's a legal position. So now your heap will be look like this. So this is 8, and the 3, 2, 5, 6. So it's a legal heap. All right. So the add operation will be always add to the from left to right. So for example, if I'm trying to add 15 here, from left to right, this one at this layer it's already full, so I'm going to add here, add 15 here. Then you need to compare 15 with this root, say 3. Okay, have to swap you, so put 3 here, 15 here, and compare 15 with 9, have to swap you. This is 9, this is 15. Then compare 15 with 10, have to swap. This is 10, this is 15. So now let's take a look at the result heap. That would be 15, 10, and 9, and 3, and 2, 8, 5, 6. So you see it's a legal heap now. So now let's try to analyze the performance. For a heap, it's always a complete binary tree. So the operation to move the item up or down, that's like for remove, you need to examine it to see if the possibly move it down, but the worst scenario will still be log 2 to n. And since this tree shape is perfect, almost perfect, it's a complete tree, so you always get the log 2 to n performance for add and remove. So we can see the advantage of using a heap to model a priority queue, because binary search tree give us log 2 to n performance only if you have a good shape. But the advantage of binary search tree, if I want to say display all the items in the heap in priority order, this in the priority queue in priority order, the binary search tree implementation will give us a sorted order, but this heap we don't get that. We only get the fast add and the fast remove. But good thing for priority queue, we only care about the add to the queue and the remove from the queue. But if you want to support an operation that display all the items in the queue with priority value sorted, then you don't get that from the heap. Thank you.